So I'm going to continue to talk about curvature. So in the last lesson, I was talking about how to introduce curvature for a curve in an n-dimensional space. Then we focus on two-dimensional space. And today we're going to be talking about the curve in three-dimensional space. So first of all, let's consider curve in Rn. Okay, so there's no need to fix a dimension. So this is a parameterization gamma, right? It's from a unitable. The picture here, we assume that it's S is the arc length. Okay, we know that. Let's quick review. We know that. So this is going to be 1, so you differentiate, right? Differentiate both sides with respect to S to get twice, and that's going to be 0. So that tells you this is a perpendicular to the curve, okay? To the tangent vector. Okay, this is a gamma prime S. So we have another vector, gamma double prime S. It's perpendicular. So this is so we introduce a curvature. It's going to be the length of this second derivative. We also derive the formula to calculate the curvature when S is not a arc length parameter. Okay. So in general, we have. Let's focus on this first. Just use a nice, arc length. Okay, that's a parameter. Right. So now I'm going to introduce a notation and let Ts to be gamma prime S. So it's the curve, right, which is denoted by T. T means tangent. Then I know we assume that the second derivative, assume that the curvature is not going to be 0. Okay, at that point. Then in this case, you get a unit vector, which is going to be gamma, this is going to be second derivative, normalize it, right? So this will be extended with NS, okay? Right? So then you can express it in the form KS, NS, okay. Right? So curvature tells you how curved the curve at that point. And but that's not enough, you know, for curve in three-dimensional space or in high-dimensional space. The curvature itself does not uniquely determine the position of the curve in the space. Okay, in dimension n greater than or equal to 3. Okay. Well, let's take a look at dimension 2. Right, if dimension 2, and then the curve, you know, basically the curvature uniquely up to transformation. Okay, so the curvature uniquely determines the curve if you're given the initial direction and the point. Okay, the curvature, okay, Ks uniquely determine the curve. Okay, we will say that up to a transformation, up to a translation. Okay, so it completely determines given point, given direction. There's a unique curve so that the curvature is going to be the given function Ks. Okay, that means, okay. So if you choose different point, different location, then those two curves you're going to get are really exactly the same, just a different location, different direction. You can rotate a little bit and that coincide with each other. All right, that's your first point. And then how about dimension 3? In dimension 3, I have to say that that's more freedom for the curve can go. So the curvature itself does not uniquely determine the curvature as a curve, right? So given a point, given direction v, you can say unit direct, okay? Given point t. So this is in R3. So you have a 3 dimensions here, right? Okay. I have to say that the curvature Ks, okay, does not uniquely determine a curve with curvature equal to Ks and initial condition, initial condition, okay, uniquely curve. So I'm going to denote by gamma s. So S is 0 equal to T as current. Okay. We're going to, how to see that, right? We will see that later, okay? So that means there's more freedom, to go, because you can draw a plane. You can draw a plane, and there's a unique one in the plane, okay? There's a unique one in the plane. But if I turn around the plane, okay, then I get another. I can draw, so the vector v is still in the second plane, but in that plane, I also can have another curve, right? With the same direction, sorry, initial point, right? So let me draw this is a new plane, right? I'm going to put the color here. Right. So I just take a look at 2 planes. Right, so for the in the yellow plane, I can maybe get a curve like that. Those are both, both curve has a curvature K of S, and K of S is a curvature, and they have the initial point, same direction, 3 dimensions. So the plenty of curves was there are plenty of curves. Right. But then you say that, well, it's not unique, but I still can locate it, right? And put if I locate, from here to here, then still they coincide. So essentially, the shape of the curve is still the same, but just have more freedom to locate. But at least I can tell you it's not uniquely determined by this initial there. Okay. It's not uniquely determined by this initial. But I can draw another curve. Cannot be obtained from any of this by locating, and then still have the same curvature here. Okay. So this is a challenging problem now. How do we study such curve? Okay. So I'm going to let gamma s be a curve, parameterized curve in R3. Okay. And we assume that it's always identity equal to 1. Okay. So the S is the arc length. Okay, it's called unit speed. Unit speed. Right, so unit speed. So step by step, okay, let's check. So we let Ts to be gamma prime S. Okay, so it's unit tangent vector. And then Ns to be, of course, you have to assume that the curvature never be zero. Okay, so that means we assume that we have to assume another condition, otherwise we cannot. Okay, we have to assume that this is the first condition. Second condition, the curvature is not going to be zero, no way. Okay, then you can define another vector, Ns. Okay, so that the second derivative can be written in the form. This is what I did at the very beginning of the class. All right, now in three-dimensional space, there's another unique vector, which is perpendicular to each of them. We call it ds. Okay, so we let ds to be the cross product of these two vectors. Okay, once you expressing that, okay, then you have a frame, right? Right, in the space, you can use the right hand to get, rotate from that and get the vector B. So you can also write NS. NS can be written in the form, I think then NS is going to be DS plus TS. And then TS could be, how can I get TS? Okay, I think TS is going to be S time plus product with NS. Okay. Yeah. Yeah, TS. So this, you get a frame, orthogonal frame is an orthogonal frame at gamma s every point. So when the point is moving, this frame is moving and rotating, maybe this around, okay, right? So maybe here, this will be like an N, and then this will be still T. Maybe this will be, B, something like that. But anyway, it's rotating. What is always fixed is a T. T is tangent to the curve, but the B and an N can rotate around when you're moving this point, right? So B and an N can rotate. B and an N can be rotated around this curve. T is always tangent to the curve when you move to the point. Okay, so this is a orthogonal plane, and T is always tangent to the curve, and then N is here and B is here. But this could be rotating, when you move the point around the curve. Okay. So this is a this is a picture. Right. Now we are going to, what are we going to do next step? We're trying to find the derivative of each vector function. Okay, so let's take a look at what is the derivative of TS. TS is nothing but the gamma prime S and prime again, which is going to K S and S by definition, right? Of the curvature. Great, no problem. All right, so I begin with, then I talk about N, okay, B. I'm going to look at the B first. B is These are TS times NS, right? So I'm going to differentiate. I'm going to differentiate B prime S by the product law is T prime S plus NS plus CS plus NS. Okay. So what is T prime S? T prime S is TS NS, right? And then TS and prime S. Okay. So this is going to be 0. This part is going to be 0. Right, so this is going to be 0. Now, we we have to say a few words about, so BS, what is BS? Where is BS? Okay. I think BS is a tangent to BS, you see, B prime S, because of B is a unit vector, it's definitely perpendicular to BS itself. Why? Why must be perpendicular to itself? Because BS dot BS is going to be 1. When you differentiate, you get this. So that's why BS is perpendicular to BS prime is perpendicular to B itself. But from this identity, right? By this identity, you will see that BS is a cross product TS times NS, right? So that means B prime S is also perpendicular to TS, right? This is by star, right? Right? It is, a cross product vector is perpendicular to each of the vector in the cross product. So that means they only have 3 vectors there, okay, right? You only have 3 vectors here. This is a T, that is a B, that is A. So B prime is perpendicular to B, perpendicular to T. So that implies this is a proportional, right, parallel to NS, right, some direction. So now you introduce a new quantity. Right? We define new quantity called torsion, tau S, by the following formula, by the derivative n. That's going to be negative and NS. Okay? So we introduce a new parameter. Okay, we introduce a new parameter. So now we already find out T prime. T prime is going to be this. Then you have a B prime going to be this. Now you get two curvatures right now. 2 geometric quantity. One is called curvature and one is called torsion. Okay. Then we come to the point about N prime S. N prime S is not going to be parallel to any of parallel to C or B. So we can write it like XS, CS, YS, and the BS. So why not? There is no N, because N prime S is going to be perpendicular to N. Okay, since you can always, since N prime S dot NS is going to be 0, right? So let's determine the coefficients. Okay. Yeah, let's determine the coefficient. Okay. But go back to identity we already got. We have this, right? We recall by star B prime S is going to be TS times n prime s, right? We already have here. Okay, so n prime is going to be t, so t cross t is going to be 0. So if this is going to be ys and ts and bs. Okay, so as a term is 0, t cross t. Yeah, replace this by this. Okay, so only y survive. But on the other hand, we already introduced a new notation called s and right ns. Okay, so let's see what is the relation between those two. So let's go back to t, and that's n, that's the b, right? So t cross b would be negative n. Okay, so compare both sides, you will get ys ys. Great. Okay, so now let's go back. I determine the coefficient here, ts plus ys and what is that? T and the bs. Okay. Yeah. So now we have one more coefficient to determine. We don't want to introduce a new variable, a new quantity. I think the k and the tau is enough. So what is this? Right. So we can do like this. I multiply both sides by a dot product, right? So n prime dot ts is going to be this, right? So dot product ts dot ts plus ys vs and the ts, right? And this is going to be 0. That's going to be 1. So finally, ts is n prime s ts. All right. So now I'm going to by the product rule, right? The differentiate that and minus. Okay. But this is going to be 0. So that's going to be ns. But what is that? That is going to be ks ns, right? The first equation we got. So finally, you have this and the length of n squared. So we get everything now. Okay, let me write down the formula. Negative ts plus tau s and dn. All right, so we have 3 equations. Let me summarize all the equations here. So you have a frame, but this frame now I have 2 equations here, n, this is b prime s is going to be negative tau s, and yeah, forgot this, right? Where it is, ns, negative tau n. Right, so then that is going to be negative ks, ps plus tau s and dn. Okay, so you have a system of 3 differential equations, and I think differential equations, the coefficients are nice, right? So from ODE for any, okay, by ODE, ordinary differential equation, okay, you can tell that given any function ks, which is not going to be 0, okay, tau s, okay, and initial value initial frame. Okay. There's a unique solution, right? Solution set. TS, NS, and BS. Satisfying the above equation we call the stuff. Okay, so curvature. So the curvature and the torsion uniquely determine, basically uniquely determine the curve, because when you get that, right, and the gamma s is nothing but the integral of the curvature, the top, okay, S0 plus S and gamma S0, right? Okay. So then you can uniquely determine the curve aperture location of the point. So what that theorem tells you? This theorem tells you given point P in the space, and not only given one direction. I need the direction. I also need a frame. Can fix a frame. Then there's a unique curve. Okay, if I know the initial position, okay, this is the initial position. Okay, there's a unique curve going out. Okay, there's a unique curve going out, and so that the frame of the curve at that particular at the point matches with the yeah. Anyway, you get curvature and torsion. Okay, so that there's more than that, right? We get so you can solve for the curve. Okay, you choose a point, choose a frame at that point, orthogonal frame, and one of them is one direction is called the tangent. That then there's a unique curve going out. Okay, so that the curvature is going to be K and the torsion is T. So that's a unique curve. So this is a unique theorem. Okay. That's a unique. Yes. Okay. So now you have a torsion, and let's go back. Okay, so you have a curvature and a torsion. That tells you the uniquely determined curve up to its initial position. The initial position and with the direction. Okay, so you have to be not only just choose the tangent vector, you have to choose a frame at that point. Then you can uniquely determine the curve. Okay. So initial data plus a curvature plus distortion and plus a torsion, you can get unique curve. Now let's understand the geometric meaning of the torsion. I know the curvature, right? Kind of, we know that. Okay, the geometry. In order to understand geometric meaning of the torsion, let's look at the first case. Geometric meaning of torsion. Okay. To understand that, we just needed to prove. Okay, we assume the first case. We assume that the torsion is identical to 0. If the distortion is identical to 0, then what we can get? Okay. Then we get, I think the above formula becomes right? It's a negative, right? B prime is going to be 0. N prime is going to be negative Ks Ts. Right. All right, so let's we have to understand the meaning of this, right? The meaning of this. So we take a look at see what we can get. At least that I can get ds is going to be the constant factor. Right, because the derivative is here. Right. I want to claim that the gamma s is a plane curve. How do you see that? Let's try to see how do we find in order to prove its plane curve, right? I need to take a look at see in order to prove its plane curve. So we have to find out the normal vector, right? So probably this is going to be the normal vector. Okay, think about, right? If this is a t, that's the n, and if it's plane curve, right? B is going to be the normal vector of the plane where the curve is. Right? So to prove it's a plane curve, I needed to assume that gamma s dot ds. Okay, let's consider this function. Okay, consider this function. Okay. So it's not going to be perpendicular, it's not going to be always 0, but I'm pretty sure it's going to be constant. Okay, so f prime s, right, it's going to be gamma prime s on ds. Okay, and plus gamma s b prime s. B prime s is 0, so this is going to be 0, right? And this is gamma s, and this is going to be 0, right? Because by assumption. So that means a 0 plus 0, it's a 0. So this is going to be constant. Right? Constant means gamma s minus, since bs is already constant, right? We can assume that this is just a fixed n. I'm going to let this to be n. n is fixed, okay? Right? Yeah, so this is going to be gamma s not b. Since b is a constant, right? So we assume that bn it's a constant, independent of s. So gamma s dot n equals gamma s 0 dot n. So that means gamma s minus gamma s 0. Okay. So that indicates gamma s is in the plane, passing through is in the plane. Okay. Passing through gamma 0 with normal vector n. Right? Because when you look at the picture, right, this is an n, and here's a curve, right? So the difference. So this is the difference. This is perpendicular n, so it's in the. So that forces gamma s is in the plane. So it's a plane curve. All right, so we prove that it's a plane curve. Okay, of course, uniquely determined by the curvature. What do we want to do here? Well, we claim that this is a plane curve. That's it. This is a plane curve. Right? So the end of the curve. Now further, what we see if moreover we assume that we can assume that we claim this is a geometry meaning, right? That's the first one. Second, we assume that curvature is 0 and pi is 0 and the ks is a constant. Okay, and this is going to be it's a constant. Let's assume it's a constant. Constant, not equal to 0. Okay. So now it's a plane curve, right? It is a plane curve, and we know so it's a plane curve. And the T prime S is going to be K. Okay, and we don't have a second equation here. N prime S is related to 0. Yes. Okay. And why this is eventually gives you a curve in the plane. So I can try it like this. This is a plane, so I can choose initial frame. I can choose the initial frame. So initial frame, the initial frame is C naught, right? And N naught, right? Okay, so this is the initial frame. So with this initial frame, I can write this as write as AS and BS. Okay. Then NS, because that's according to definition, it's going to be like that, located by 90 degrees. So NS is negative BS. Yes. Right. Yeah, it's located. This is a T, this is a T, and this is N. Oops. All right. So according to above the equation, you plug them into the above the equation. So you will get, okay, you will get A prime S, B prime S is going to be K naught, right? And negative BS, BS plus AS, okay? So you will get A prime S equals negative K0 BS, and B prime SS equals K0, K0 of AS. And we know how to solve this equation. Okay, since it's unit vector, okay, it's going to be 0. We also know that AS0 is going to be 1. BS0 is going to be 0. Okay, because from the above expression. Okay, so the unique solution, I think it's going to be cosine okay, when S equals I'm sorry. Okay. I think so. Yeah. So when you differentiate, you will get negative differentiate. You get negative K0S sign, which is BS. When you differentiate, next one you get it. So this is a unique solution. Unique solution. Now, once you get that, then you find out TS is just equal to cosine okay. And this is nothing but this, right? So when you integrate it, you will get a formula for the gamma. Okay, that's the initial point. And the integrate of a sine, cosine, this will be sine okay, I think it's divided by enough. When you differentiate, you get the cosine, okay? Minus cosine and the Q. Okay, so this is a general formula, okay? When we have to be careful when S equals S naught, so this is going to be 0. The other one, yeah, this is it's going to be 1/4, okay? I think we have to add yeah, when you integrate, we have to add a constant here. Just integrate on both sides. So this is a curvature. This is a sorry. This is a formula with a given curvature. Okay, okay, and it's indeed it is going to be the yeah. So this is not a center. Okay, it is not a center. Okay, but if we combine those two. If we combine with this two, we call it let's call it vector. Let's denote it by vector something. Okay. So let's call it C. Okay. Then gamma S minus C is going to be Right. So first of all, it's a plane curve. Not only have a plane curve, and the length, this is going to be 1 over 2, okay? Because the sine cosine is, so you can square it and add them together. So it's constant. This is the radius. So it's not only it's a plane curve, okay? This is a vector. This is gamma s. So the difference is the radius. The radius is 1 over 2. Okay. Okay. It is a curve. It is a plane. It is a circle on a plane. Okay. It is a circle on a plane with radius r. Okay. Okay. Let's go back to the problem again. So we're trying to determine the curve completely. Like torsion 0, curvature is constant. Then using the above formula, we find the first way it's plane curve. Then we try to solve this equation and use the initial data. Okay. Then you basically want to get this one. Okay. So you get a coefficient A and B. I can solve it. And then I put there, and then I also get a general formula for gamma s. Then I realize that this gamma s is indeed a plane curve, because if you move this, if you denote this part by c, then you move to the left-hand side, and this will be a combination of sine cosine, two vectors. So anyway, it's unit vector. The length is going to be just is going to be constant 1 over 2 here. All right, so that is about the plane curve. So the geometric meaning of the plane curve when torsion is not going to 0, it is going to be like that. Okay, if a tau is 0, it's a plane curve. Plane curve. If tau is positive, that means it's not only curved, but it's going to be a lift in the plane. It's lift going up, okay? And then curve, rotating maybe. This one is completely in the plane. Okay, that's the geometric meaning of the torsion. Okay, if you look down from top, okay, the projection, the shadow, is a plane curve, and the curvature, I think it's K. Okay, then but it's also going up. Okay, it's also going up when tau is positive. Okay. So to understand better on this portion, we have to look at an example. Now, when you do the computation, sometimes you have to normalize to it to that. You have to normalize, to the arc length. Sometimes you can do it, sometimes you cannot. Okay. Okay, so let's try this. Let's look at the example. Yeah, if you use the definition of the torsion, you have to reparameterize it. That's okay. Gamma theta is going to be A cosine theta and A sine theta and B theta. Okay. This is called a circular helix. Okay. Now, theta is not going to be the arc length. So in order to compute K and the torsion at the point the gamma theta, we have to make sure we can find the arc length as a new parameter. Okay, then you follow the definition you can get. But let's try that way. I remember it has a constant length. Okay, it has a constant length. So it's going to be negative A sine theta, A cosine theta, and the B. So the length is going to be square root a squared plus b squared. So it's constant. Good. So s is going to be integral from 0 to theta. Let's say I'm going to use a different notation. Yeah, you cannot use theta here, b there. Okay. So it's constant. So it's a squared plus b squared equal to 10 times theta. So that's the relationship. So if you change theta to s by this formula, you're going to have a constant speed. Okay. So theta is going to be s of this, right? All right. Now you use a new parameter. You can use a tilde here. It doesn't matter. Yeah. Usually you can change the notation. Otherwise, it's the same gamma. So that is going to be theta, right? And the theta is replaced by s of this. So it's going to be a cosine s d sine s over square a squared plus b squared and what is it? Oh, that is yeah, this is a scale a, this is a b. B theta is s. Okay, so this is arc length, okay? Unit speed parameterization for the same curve. Now you can use that to calculate everything, okay? First of all, TS, right? Right, they already have a formula. And then we differentiate. And we differentiate. We can calculate the A and the B, you know, and the friend. Right? So when you differentiate again, so first of all, let's differentiate one by one, you know, otherwise I cannot do this. So a, negative a, square a squared plus b squared, and sine s, right? And here's a cosine s, s squared plus b squared, and the c, where's my, yeah, that's going to be, this will be constant. Okay, so that's the first derivative. Second derivative, so that's my TS. So I'm trying to find the TS and the you know N and the B, the friend. I'm trying to find the friend. So when I differentiate again, I find out this is a here a squared plus b squared and become cosine. Okay. Then I got negative a squared plus b squared sine s. And the third one is 0. It's constant, so it's 0. So that is my, not my n yet. Remember, the n is, you have to normalize the vector. So the curvature is constant. Okay, the curvature is going to be constant. Right, do you agree? The curvature is constant. Just the length of this vector. Right, it's constant. The constant means it's a low, it is curved evenly. Okay, it's curved evenly. So ns is going to be, you have to normalize it. So you cancel the constant. So it's negative cosine s squared plus b squared and sine s square a squared plus b squared and 0. Okay. So let's take a look at the geometric meaning of this before we move on. Okay. So this is a picture. Okay, I'm drawing the cylinder here. Okay, this is a curve, rotate. Okay, and this is a tangent vector n. It says that the normal vector perpendicular to tangent vector is always horizontal. That's a key point. This is a horizontal because the third component is going to be a 0. It's always horizontal. I pointed to the axis, the y-axis. as the z-axis. Okay, it's a unit vector. Okay, and the curvature is dependent on a, right? A square over a square plus b square. Okay, and it's curved evenly toward the. So if you look at the projection of this curve onto the xy plane, you get a circle, right? Circle was a certain radius, okay? Yeah, the projection is going to be circle with radius. This is r, right? R is going to be a. I think so. Yeah, the circle has a radius I equals a. Okay, but the curvature of the circle is a. However, the curvature of this curve in the space is not a. It's a over a squared plus b squared. The curvature, right? So the curvature of this circle K, this circle K, okay? Especially it's going to be 1 over a, right? And for the circle. But the curvature of this helix is a over a squared plus b squared. It's a smaller than, if a is positive, assume that. If it's smaller than 1 over a, okay? Because it's denoted, it's smaller than a over a squared, which is 1 over a. So it's not, that curvature, it's constant of the helix. The curvature of the helix is constant, but does not equal to the curvature of the curve under that, of the circle under that, okay? But anyway, this is, so let's move on. So then we are going to get the normal vector B, okay? Now in order to find the torsion, yeah, how to find the torsion here? We want to compute the torsion. You can find the B first, and then you differentiate, right? Based on our formula, right? We call the formula. We call the formula. Which formula we're going to use, right? We call the formula T comma equals Kn, right? N comma equals negative K top plus, okay? And then T comma equals negative N, okay? To find the torsion, I can find the N prime, and then you multiply by B. But anyway, I have to find the B anyway, right? Yeah, so torsion can be N prime times B, right? Or it can be, from secondly, it can be B prime times N and multiply by -1. So either way, this is the same. So we have to find the B anyway. So it depends then whether we are going to easily, yeah, we have to find the N. N is going to be T cross N. It's going to be I, J, K, Y, okay? So what are the components? I forgot what we got. Okay, we have to go up. Okay, let's memorize that. T, okay, the coefficient here is going to be negative A over square root, okay? Negative A over square root, A squared plus B squared. And that is going to be, I think it's sine, right? Sine, and cosine. So I'm just simply going to sine something, okay? For the simplicity, A squared plus B squared, and the cosine something. Then here's B, A squared plus B squared, okay? So that's what we got, right? We don't need to know the exact value of theta. Let's double check everything's fine. Then N is negative sine and the cosine, negative cosine and sine, negative cosine of this, negative sine of this, and 0, okay? So now we are calculating. So let's look at this. It's going to be B sine of this I, minus, minus let's take a look at this. This is going to be really positive. It's yeah, it's cosine of something, okay, J. And then the last one is going to be, I think, is and the sine square plus cosine square is okay. So you do get a vector, you do get a vector, and that's a B, okay? So we can write the vector in this form. Okay. Now this vector is perpendicular to what? It's perpendicular to T and N, okay? So let's double check whether it's perpendicular to T and N. It's perpendicular to, this is a minus, when we do the product, okay, sine is sine square negative, so negative AB on the top, right? Negative AB and plus positive, so it's 0. Okay, then the sine cosine, it's 0. Okay, so this computation is correct. So this is my BS. So we find the BS. Right, so we find the BS, and then I'm going to differentiate. I prefer to use this formula to find the top. Okay, I can differentiate n, but no, I don't want to differentiate n. Then use a dot product. Doesn't matter which one you're going to use. Okay, so use a differentiate this. So this is going to be s, right? Square a square plus b square. When you differentiate, you will get b. Okay, and this is a negative, so it becomes b a square over a square sine, and that's a 0. Okay, so this is supposed to be called negative distortion and n. Okay, so what is our n? Our n is negative of this, right? So it is clear that, yeah, it is clear that distortion, remember the n is only this part, negative, right? So it's going to be, it's going to be negative cosine something, negative sine something, and 0. That's the n. So compare both sides, you will get, this is a distortion, okay? So we calculate distortion. And that's it, this is also constant, right? So that tells you if B is not equal to 0, then distortion is not going to be 0. So it's it's constant means the curve going up at the constant rate. Okay, it's going up. How is it constant? Okay, going up at the rate of this in some sense. Okay, and this is a K. It's curved in that form. It's A over A squared plus B squared. Right? It's curved in that. It's also curved toward the y-axis, z-axis at a constant rate. Okay, at a constant. Okay. So curvature, let's understand the meaning of curvature and torsion. It's like, yeah, the meaning is like different. If the point is 0, that means this is a curve not going up, or they always stay in the plane. If point is positive, means going up, and same time it's curved, locate, right? Finally, I want to talk about the formula. What happens if we want to find a formula to calculate? Okay, if P is not an arc length, okay, let gamma T be a parameterized curve. Okay, and T is not necessary the arc length. Okay, so that means gamma prime t, I'm going to use a dot notation. We just spoke for general one, it's not use a prime. So you can tell the difference. So the length is not necessary to be 1, even constant. Okay. So in that case, how do we solve the problem? I don't have much time left, but as long as it's easy to derive the formula, let's see. Yeah, I can finish it. Okay. So first of all, I claim we have square. It's the same. Okay. Let's see, same. Okay, where gamma prime s is the arc length. Okay. So when t equals cs, and you reparameterize. So as long as you know this is true, then this actually gives the formula for the torsion. Okay. If this is true, okay, then what do you get? If this is true, then this identity true, then it gives the torsion up. Okay, and the y. Let's look at the quantity on the right hand side. Let's look at the quantity on the right hand side. Okay, t prime theta is going to be tau. This is t, right? And the gamma double prime is going to be ks and ns. So the cross product is going to be ks and the cross product. And this is just the ks of b. Okay? Okay, right? Then let's take a look at this double prime, triple prime. Triple prime is ks ns plus ks n prime s. So that will be k prime s ns. And we already know, the derivative of this is nothing but negative okay. So so what? So you have k prime s and s, right, and negative ks square ps and plus ps tau s ds. Okay. So that's the third derivative. Now let's take a look at the product. The dot product, you will see that B is perpendicular to that. B is perpendicular to that. B is not perpendicular to this. So what do you get? You have a ks, and the torsion. That's it. So this is what we get here, right? But on the other hand, this is going to be ks, right? So the quotient gives you a torsion. That is when it has unit speed. Okay, so this is just the torsion. So use this formula, and you can calculate the torsion. Okay, but this is arc length special. But if you prove this claim, and you can change it to any variable. So this quotient is independent of the parameterization. This formula. Okay, so you can use this. This side is this side is a torsion actually. However, so torsion is given by this formula. You can use, so given arbitrary parameterization of the curve, you can use that formula, differential 3 times, and then you can always get the curvature and the torsion. Okay, so we can, at the end, I don't have much time left, I'll just say we can use the formula to compute K, okay? Compute the torsion at gamma t. As this torsion is going to be arbitrary derivative. No, arbitrary parameter. Okay. So anyway, we have we learned the two geometric quantity. One is called the curvature, other one is called torsion. The geometry meaning, you have a pretty good idea right now how it's changing, right? The torsion just tells you how fast you can lift the curve from the plane, getting away from the plane. It's away from the plane, being a plane curve, And the curvature really tells you how the curve is curved, okay, in a plane, okay. So so then we try to find the formula, different formula to compute that. And this is we always try to find formula, even the quantities defined using the arc length, right? Then we still needed to find another formula to do the computation. Use it to find to compute the curvature, and the torsion. Okay, this is a pretty good useful formula. Okay. That's it, and we stop here today. And I hope you will. The homework I got, it did pretty well. Okay,